So my name is Nijas. I'm an application engineer coming into electronic design challenges, right? It can be from consumer or industrial application, automotive, aerospace and defense, electrification, 5G or ADAS application. If you see the cost or the main requirement to achieve for these kind of application, most of the places they you will see same similarity. You see cost reduction, connectivity, product performance, thermal management, energy efficiency, and same if you see coming into automotive, you can see same kind of a requirement. So where you go in any of these application area, either automotive, aerospace and all, the requirement and specification or constraints to meet while they make a product, they are more or less same. And here and there you will see some difference because of this require the total industry change. And when you see these all these challenges, and it all requires kind of electronics products in it. It's all start from the chip, package, board, assembly and all. And in today's presentation, we will discuss about two aspects. One is called reliability, another one is called integrity. So very simple way, a person who is not familiar with this term, integrity stands for whether if I make a product for a consumer electronics or automotive, whether that going to work now, that indicating the integrity. So if I make a product, if it is not working today, then I can say it's not meeting the integrity of that product. The reliability means how far in the future it can work. Can I use this phone or laptop for 5 years or 10 years, or I can use only for 2 years. That means the reliability. So we do have a tool which can do the integrity, whether your product going to work today. It can also predict how long your tool going to or the product going to last. So that is what the whole presentations today is going to help you. So let me talk about few things on the integrity. And when it comes to electronic side of this whole spectrum, that consists of a PCB, right? This is well known for most of the electronics people. You will have multi-layer PCBs consist of a IC. So inside IC you will see a die, then you will see a package which is covering the die and a lot of pins which is connecting to the PCB. Then you have the bare PCB. On top of the bare PCB you will have a lot of inductor, capacitor, resistors and other thing. And sometimes you need to have a wireless connectivity, then you need to have an antennas on top of it. And moreover that this PCB has to work with the DC, where we have a general purpose AC, either 110 or 230 volt AC, that to this particular power section will convert the AC into DC, and that going to power up all the IC components or all the components in the PCB. This is what a general PCB will look like. Let's see what all kind of the simulations we can do for integrity and reliability side. So for a very high level point of view, there are a few terms called signal integrity, power integrity, MIMC. Very simple way. Signal integrity stands for if I send some signal like digital data ones and zeros, whether that's going to receive the other end. Let's say from processor to memory, you are sending some ones and zeros, will be able to receive and decode that same information at the other side. That is what signal integrity stands for. But the power integrity is mainly take care of power distribution. So you can see a lot of IC going to place over here, right? And this will all supply the power from the DC-DC converter or AC to DC converters. So whether these powers are going to deliver sufficiently, will that going to create any problem? That is what we do in power integrity. EMI-EMC stands for we are intended this PCB for particular application. For example, you made one PCB for your vehicle electronic ECU control board. It's not intended to radiate or create a problem to any other devices. So in EMI-EMC, we will check whether your device is going to create any emissions, or is there any emission coming from nearby things, whether my PCB going to handle it or not. So that those will comes under integrity. The thermal is part of both integrity and reliability. I will tell you why. If there is a temperature building on your system and it is going to melt your PCB or melt your IC, that's the moment you turn out within half an hour your PCB will be burned out. So that time it will comes under integrity, and it can goes into reliability, because over the time of the month or years, if it is heating, that can deteriorate your electronics performance. So that can lead to reliability also. So structural reliability, it is a different ball game. It will predict how long your PCB uh, going to perform or without any failure. That determines how long you can give your warranty for your electronic devices. So these applications comes under reliability part. Coming into PCB, normally Ansys not there in any of the PCB design application or PCB design tool. We took a neutral steps here. So you design your PCB in any of these tools which is commonly used in industry. We are ready to accept this PCB directly into Ansys tool. So either it Guidance, Zuken, Altium, ODB++, or IPC 2581, you can easily import it and you can run all kind of analysis. Coming into the workflow for signal and power integrity, it starts from the pre-layout analysis, where you will decide what should be the thickness of your nets and how many layers are there and what is a wire dimension for better signal transmission. These analysis will do in the pre-layout portions. In post layout, you will see from one IC to another IC how the signals are propagating. There are two kind of analysis we do: signal integrity and power integrity. As I mentioned, the digital signals will be checked under this, and the power which is delivering to the ICs and components will be check over power integrity. And before doing this one, we normally does something called EMI scanner, which does the PCB rule check. What I mean is, if PCB designer didn't care about the proper routing of your PCB, then this can check and tell you that whether it is going to create a problem before going for a detailed analysis. After this signal integrity and power integrity, you can do the EMI/EMC analysis. So let's see about what we can do in this particular EMI scanner. So there are some certain rules we do in signal integrity, power integrity, and EMI/EMC. Those are like net crossing, split ground, net changing the reference. So because of these reason, how much is a problem where all in PCB, let's say you have a big PCB, where all these kind of violations are deviating, it will list out all the violations, and the moment you click it, it automatically show you where it's the violation. So you can see there is a PCB net which is passing through, and the grounds are splitted over here. Because of the ground splitted, or there is a gap in the ground, there is a high electric field is formed. This can lead to the emission in the EMI/EMC point. To avoid this one, you need to add a stitching capacitor. In the stitching capacitor, it will tell you how you can see by adding the stitching capacitor, this high electric field formation is completely reduced. Now you can use it with a splitted ground. And over here, there are few analysis you can do. You can change the spacing between this stitching capacitor or ground and the distance between the stitching capacitor, and see how much is the emission it is causing by changing these values, and how you can reduce it without before going into final implementation. So a lot of initial level analysis you can do with the EMI scanner. Now we comes to signal integrity, and signal integrity side, as I mentioned, signal integrity mainly check if you have an IC on the PCB which need to send some 1010 bits to another IC. It can be a memory, it can be a connector, anything. So where the digital signals are going 1010 bits, you can run that kind of simulations using the SA wave or HFSS solver, which will first extract the S parameter in frequency domain and add all these IBs transmitter receiver combinations. These all are automated. The moment you select and set the ICs and properly setting the IBs configurations, it automatically run the time domain simulation. It will generate I diagram. So the I diagram which will tell you that if there is a good opening of I, which means the signals are going to decode properly at the receiver side. If the eyes are going to be smaller, if this eye is going to be closed, something like this, that means your signal integrity going to be worst. And it also generate a lot of complaints test report, DDR 1, 2, 3, 4, 5, and LPDDR and other things, SERDES analysis, and it also create a report out whether your which all nets are passing, which all nets are failing for this signal integrity sign of a application. Another kind of application is which is very common for the electronics gadgets is a flexible PCB. So when you have a flexible PCB, you can design this kind of movements and rotations and bending, and you can see how the eye diagram is going to change when you fold it in different angles. So you can see right now this is better, and when your the PCB is bending very tight together because of the cross coupling, your eye became close and close, and you are losing the communication. So you can virtually verify this kind of flexible PCB using tool. Coming into power integrity, so I mentioned most of the time you might have seen the PCBs are getting burnt out. That most of the time happening because of the DC power consumption of your IC. So you will have a DC like 5 volt or 3.3 volt generator, which will carry the power to the voltage your positive and negative like ground and VDD pins, which will comes over here. And if your current is drawing is very high, what will happen? Where all your current is going, you will have this kind of a direction, and where all the currents are crowding, those areas you may get more heat, and you can predict the voltage drop, current crowding, and we also calculate something called the natural resonant frequency of the PCB in terms of frequency, at what frequency your ground plane and power plane going to resonate, and that also intent finally into EMI/EMC application. We do decoupling, capacitor optimizations, and temperature predictions and all. So how the temperature prediction happening? There will be a detailed session on this particular topic. Since power integrity is very much connected with thermal, I'll share one slide on thermal side. We calculate the electromagnetic losses in your PCB using the EM solver, and send that RF losses, distributed RF losses. You can see this losses is over here on your multi-layer PCB. That losses will come to thermal solver. It will predict what is the temperature going to happen or generate on your PCB by taking care of DC consumption of your IC points, and it will send the information back into EM solver. Why we need is, what happened is, assume initially it was 20° thermal solver predict 45°, but at 45° your PCB material property is going to change. So after the spatial temperature property came back, then the EM solver will run one more time, predict the RF losses based on the new updated material based on the temperature. Again, the power loss will come. You can run one more time thermal simulation. So 45° going to change to 47°. If you want, you can do multiple time of iteration, which will predict the temperature similar to the practical thing. So you can have a big rack or big server room. There's no limitation. It can run and take care of things well. You can keep your PCB, multiple PCB, heat sinks, the exhaust fans and other thing. And you can place this PCB inside a thermal solver, and it will predict how the temperature going to finally generate with the heat sinks and external fans, and how the airflow is going to happen from one side to another side. So these all are the major analysis we do for electronics PCB application. Now coming into RF and RF applications, where most of the people need mobility. So we used to connect all the communication through LAN cables and other thing. Now everybody need a mobility, they need a wireless connectivity. When the wireless connectivity comes, the antennas and antenna arrays are going to be the major player in the wireless communication side. So you can design the antennas, you can design phased array application, you can do a lot of military defense kind of application like RCS, antenna placement on different ships, aircraft and other thing. You can use the antenna for mobile integrations, biomedical application like MRI and other thing. And if you want, you can even integrate your antennas on commercial platform like a printer, your wireless like controllable ACs, the IoT devices and all. So in order to do this one, sometimes PCB you see most of the time it is smaller, planar in shape, whereas these kind of geometries are sometimes it goes for meters and hundreds of meters. Sometimes we need to simulate for kilometers for an entire city for communication purpose. For that, we do have a different solver for simulating such things. Very complicated antennas and the smaller antennas, everything you can simulate using finite element method. If you have a bigger things like a big aircraft, big automotive antenna, and this portion of a buildings and other thing you can simulate with the method of moment. If you really want to simulate a city where the vehicles are moving here and there, and you wanted to see the coupling and the connectivity, you can use shooting and bouncing ray solver. So it is a combination of multiple solver in a single GUI, and it can even do the hybrid simulation. That means a part of body can be simulated with the finite element method, and remaining portion can be simulated with a different solver. It can be integral equation solver or SPR solver. So a simple example which we did with the HP some time back, you can see a dual band, dual polarized antenna, and it is the radiation pattern is coming good. Finally, this antenna has to integrate with the wireless printer. So first we took a portion of a nearby printer area and see whether the S parameter of the antenna going to change or not. Then we integrated that one antenna, and you can see this radiation pattern of initial design and final design is changed a lot. That indicating this antenna is will not have a proper communication at some direction. This radiation pattern or the shape indicating whichever direction the radiations are good, and where there is a green or blue color coming up, that indicating that particular direction in the 3D space, the radiation will be lesser from that particular system. So you can see this generated very good mesh, and wherever the antenna is placed, that area you can see a finer mesh created. It is because of the adaptive meshing process which is happening inside the HFSS, which automatically find the right location where the electric fields are strong. Those area the mesh will get generate more, and other place where the fields are very weak, it will have a coarse mesh. So it does the automated meshing method, which will reduce the memory consumption, computation resource consumptions, and it always reliable in the results compared to measurement. So this is another case study with a smartwatch. You can actually draw a picture from your idea and realize everything and see how what all frequency this antenna going to work. And you can also see when the smartwatch going to be placed on a human body, how the radiation going to happen at multiple frequencies, and how this FCC specification or regulations are going to meet. Why I mean is, any devices you make a handheld or biomedic the wearable devices, that has to pass something called the FCC regulations requirement. That has a different requirement with respect to frequency. So anything which is less than 6 gigahertz has to go with the specific absorption rate. If it is more than 6 gigahertz, then you need to do the power density calculation at a certain height from your devices. So these are the requirement. The requirements are uh, well formatted based on the FCC standard. So if you have a device, you can run this SAR simulation. It will predict how much is a SAR, and it can also do the power density calculation based on the FCC regulations, and it will tell you what is the worst case of SAR based on this beam forming and other thing. We do these EM simulations for automotive. So if you take a vehicle, this is a screenshot of the HFSS and ADT GUI, and this is nothing but our sharpen antenna. People who are familiar with the antenna on top of your vehicle, this is exactly the same. It can support your GSM, LTE, 4G, 5G, and GPS kind of applications. So you can see one antenna which is marking at multiple mobile communication band, and you can see how the radiation pattern going to look like when you place the sharpened antenna on top of it. So this is based for 2.4 gigahertz. You can see what is a gain and radiation efficiency coming out of the antenna. And you can see multiple radiation patterns I have plotted here. I will show one by one. You can also see the mesh which is created for this vehicle for the computation. And this is a 2.4 gigahertz communication band antenna radiation pattern. And this is 490 megahertz antenna. This is also GSM. And there is 1.9 megahertz antenna. So the sharpened antenna normally contain multiple antennas for different applications. It can be vehicle to vehicle, vehicle to infrastructure, GSM, GPS, and many other things. You can integrate everything and see how the radiation far field, how the near field, how the surface current, everything is happening. This can be nicely visualized and validate, and its results are well correlated against measurement with the different customers. So you can see the surface current which is generating on the vehicle when the antenna is radiating. You can animate it and see how the surface current is propagating over it. Okay, so coming into 5G, 5Gs are very much demanding now with the higher data rate requirement, and you need to use higher and high frequency in order to mitigate the losses which is generating because of the distance of using fixed transmission. You need to use the arrays of antenna in order to steer the beam to left and right. If you take a simple antenna array, you will have a power divider, you will have a beamforming network, amplifier, circulator, and multiple antennas. You can visualize this antenna, how the signals are going to propagate, how the signals are going through the amplifier, phase shifter, circulator, and finally it's going to radiate, how the radiation pattern going to be. So you can visualize, virtualize everything and make the product very easy. So two type of applications so far we discussed. One, initially we discussed about PCB, another one we discussed about antennas. So antennas in 5G, they have a capability to do the beamforming, that nothing but changing the radiation direction without changing the geometry in mechanically. So electrically steering the radiation pattern. So for this example, you can see a mobile with a PCB which carries the digital data, and in nearby there are antennas. In our practical mobile devices, there will be multiple PCB, almost 5 to 10 antennas are there in a small handheld devices. There can be an interference between the antennas to digital and digital to antennas. Both can be creating a problem. So we can create that kind of environment in simulation, and this is telling when the controller is sending ones and zeros bit. You can see the eye opening is very good. That means the digital data are able to send from the controller to memory without any problem. When this is the time when the antenna arrays are off. Okay, when antennas are on, both are on, your digital and antennas are on, you can see when the antennas are beamforming towards the PCB side, you lost your digital communication. That indicating the antennas are going to interfere with your digital circuit. So you can visualize this kind of thing in measurement. Measurement is difficult because your antenna may steer to all the different direction, and only at particular direction only you are seeing this eye diagrams are going bad. Rest of the other direction, when it is radiating, it is still able to communicate. So this will help you to decide whether you need additional shielding on your digital circuit to protect from the analog, the RF radiation. So that was a simple MIMC or RF interference problem. We need to pass all our electronic devices under the MIMC regulation standard. That can be an emission. The emissions can be conducted emissions, radiated emissions, and these are the problem when your devices are start radiating and creating problem to others. So it should not create a problem, or if it is radiating or conducting noises, it should be within a limit. There are some limit for each, standards are defined. So that this is indicating how bad your device is going to perform or radiate outside or conduct outside noises. Then the second one called immunity. Normally, if somebody else is radiating some noise, how good your device is able to handle that kind of noise. So the noise can be injected to your cable, the power cables, whether your device is going to perform well, or a radiation coming from air, like as a radiated noise incidenting on your device, will be able to handle it or not. So we do all kind of EMIMCs tests from the PCB level, PCB plus cables and LIS, and even you can do the full system 3D simulations also. It requires a lot of components because EMIMC is a PCB plus antennas plus cables, everything together. So to do the EMIMC standards simulations, you need to have multiple components to model the complete electronic devices. That requires LIS and requires a lot of testing antennas and waveform generators, characterization of active devices. All these toolkits are available under the HFSS or ADT, that you can use it for conducted emission, radiated emission. So here you are seeing the work we did with the Rockwell automations. On the conducted emissions, you can see the red one is a measured one and the black one is a simulated one. So the trends are exactly matching along with their peaks. And if there is a peaks are going well below above the limit line, you need to reduce it by using filters and shields. So this is the images showing by adding the filter and shield, how much you are able to reduce the emissions in the conducted range. And you can also see the measurement and simulation correlation on the radiated emission side. Similarly, you can do the immunity analysis. This is an example of a ESD EMIMC. So ESD gun is injecting, and you are checking the coupled vertically coupled field on your coffee can machine, and you can see with and without ground how much you can reduce the induced voltage on the PCB. So this is talking about radiated immunity when the antennas are radiating and your devices is on the table, and how much is the table and cable is going to pick up. And conducted immunity side, you can see the bulk current injections, and you are checking what frequency this device is picking the noise into the PCB. So some other analysis is consists of a full system level simulation where you will have a vehicle. It can be aircraft, it can be spacecraft, it can be automotive, it can be anything, which consists of multiple cables, PCB, and sometimes antennas also. So you can see vehicle which carries the cables, motors, PCBs, everything, and inside top of that there is an antennas also, the shark fin antenna, say a simplified version of shark fin antenna here. And when you model everything, you need to model your LIS and cables, motors, bus bar, inverter, everything you need to model in the circuit. And these blocks are coming from the EM simulation side. You combine all this simulation, and finally you can predict how much is the emission coming out at LIS and when these things are radiating or the cables are conducting. The system level analysis also you can do it with the tool rather than go for a measurement. You can do everything virtually.